All right. So here's the clever math that Michelson came up with his apparatus there. So ultimately, you want to calculate speed. It comes down to two things. You always need a to find speed. You always need a distance and you need a time, and then you can take the distance divided by the time and find the velocity of anything, including light. So let's consider the distance. How far did the light have to travel in this experiment? Well, first of all, let's define the experiment. The experiment lasted from the moment the pulse of light hit one side of the eight-sided mirror until it went to the other mirror and back. So the distance is 2 times the distance between the rotating mirror and the plane or flat mirror. So if we go back to our picture, if we could find out this distance from here to here and back, so there's our distance. We just have to double the distance to know how far the light traveled, and that's what we use. So that part's pretty straightforward. Now let's consider the time. The time that it took the light to travel that distance is the time it takes to rotate the mirror 1/8 of a revolution, right? So go back and think about it. This thing hit this mirror here. It's traveling. Here, let me erase some of this so that we can see a little better. So the beam of light that we send, this little pulse of light, if you want to picture just that little pulse of light hits this mirror at this point. So it comes out here. We're not worried about this part right here. It comes down here, hits this. Now the experiment starts. The light has to travel all the way there and back. And in the meantime, somebody has to spin this mirror exactly 1/8 of a revolution so that this side of the mirror is in a position to reflect it to the detector. So the time is the time it takes to rotate the mirror 1/8 of a revolution. So if we're spinning it at its slowest, let me just explain this note here. For an eight-sided mirror spinning the slowest, you can imagine if we wanted to, we could spin it faster and faster and faster. So instead of being content with just spinning it 1/8 of a revolution in the time it takes the light to go there and back, maybe we go crazy and spin it 2/8 of a rotation. Heck, we could spin it 3/8 of a rotation at any time or any increment of a rotation. We'll get the light getting to the detector. But for the most part, we're worried about the slowest. Let's take it easy on ourselves. So usually it's 1/8 of a revolution. You can take a second to imagine if Michelson had not used an 8-sided mirror, but instead uses a 6-sided mirror. Well, if mirror was 6-sided, then now we're looking at 1/6 of a rotation. And if you wanted, we could have a 10-sided mirror. We could have any sided mirror we want. It just changes the number a little bit. So be aware. There's nothing magic about an 8-sided mirror. It's just historically, I think, what he used. But you'll see questions in which mirrors are 6-sided or 10-sided or whatever. So we got our distance and we've got our time, except the time is this weird 1/8 of a revolution. And if we go back to our understanding about periodic motion, things that are spinning in circles, often we don't talk about things like how long did it take to take 1/8 of a revolution. Sometimes we talk about something called the period. So let's remind ourselves of that. The period is the time for one complete revolution. All right. So keep in mind that if we know the period, capital T, then the time for this experiment to take place would equal 1/8 of the period, or 1/6 if it's a 6-sided mirror, if you want to go that far. So if we want to know the time and we know the period, we can do it using this basic calculation. Time is 1/8 of a revolution, or 1/8 of the whole period. Now, just to make things a little more complicated, you'll remember we don't always talk about period. We sometimes talk about frequency. But that's okay. In order to relate period to frequency, we'll remember on our data sheet, and it tells us this, period is the 1 over the frequency. So the distance is usually the more straightforward quantity to know in this experiment. Sometimes the time is not given straight away as time. Sometimes it's given as period. And then we have to convert it to the time it took for the mirror to rotate its fraction of a rotation, 1/8 in this case. And sometimes we even start further away and we're given the frequency. And by using the frequency, we can get the period because it's 1 over the frequency. Then we still have this step over here to take the period and then determine the time based on the period. So at first glance, not too bad. Distance and time, pretty straightforward. But often the information given in a question around Michelson's experiment, not as obvious, not as straightforward, makes us recall our understanding or bring forth our understanding of frequency and period. So let's take a look at an example question. All right, so here's the question. In a Michelson experiment, mirror is rotating that many revolutions per minute. So let's just remind ourselves that quantity, a couple of clues we look for, is that a period, is that a frequency? Well, consider the units, revolutions per minute. Notice that the time in the units is in the denominator, so we start to recognize that this represents a frequency. So be careful with this one. And the way it describes it, it says it was found to produce an image. Basically, what they're telling us is we're spinning it at just the right frequency, just the right period that we get this image at the detector. They identify the number of sides on the mirror. We'll be careful. It's not always 8, but it is in this case. And the distance between the rotating mirror and the plane mirror is 35 kilometers. So what is experimentally found speed of light? Well, I like to encourage students just to break it down to the two quantities that we're really looking for. We really want to know the distance and the time. In order to know the distance is going to be twice the distance between the mirrors. No official formula for this, just common sense and an understanding of the experiment. So in this case, 2 times 35 kilometers, that's 35,000 meters. So I'm just going to leave that as 70,000 meters. That's the distance that the light has to travel. Now, the hard part, what's the time? Remember, the time we're looking for is, never lose sight of this, for 1/8 of a revolution. So it might be useful to write that at the top. So given the frequency, which is 3.12 times 10 to the fourth, that's revolutions or cycles per minute, then we need to turn that into a period and eventually into a time. So the order that you do this is not critical. But what I might do right now is, I don't like the idea that I've got minutes in here, so I might convert my frequency from cycles per minute to cycles per second right away. And the easy way to do that, for me anyway, is this is the number of revolutions, so I'm good there. And I'm just going to, instead of writing 1 minute, I'm going to write 60 seconds. And now I'll change my units from revolutions per minute to revolutions per second. So pulling out my calculator here, you might hear that happen. 3.12 times 10 to the fourth divided by 60. So I get 520, and that's revolutions per second, or if you want, hertz. So that's kind of step one. Put frequency into a usable form for later calculations. Step two then is, let's convert frequency to period. Period is 1 over the frequency. So the period should be 1 over 520 hertz. And now my period, and I'm going to point this out, capital T, so I'm not confused with like any random time frame. This is the period, the time for a complete revolution, and I get an answer of 1.92 times 10 to the minus 3 seconds. So this is not how long light had to travel. This is how long it would take for that 8-sided mirror to spin all the way around. But remember, in this experiment, it didn't get a chance to spin all the way around. It only had a chance to spin 1/8 of a revolution. So let's finish this off with a calculation of the time for 1/8 of a revolution. So 1/8 of the period is the time we're looking for. So the time is 1/8 of the capital T period. So 1/8 of 1.92 times 10 to the minus 3 seconds, and we get 2.40 times 10 to the minus 4 seconds. So this example kind of splits it all out. You don't necessarily always start with frequency to get to the time, but this one shows that progression from frequency to period, period to the time for 1/8 of a revolution. And now we're where we wanted to be at the beginning. Like any calculation of speed, we now have a distance, 70,000 meters, and we have a time, and we can do the last calculation. Let's zoom in a little bit here. So we can finally do our calculation of speed. Speed is distance over time. Distance is 70,000 meters. Time is 2.40 times 10 to the minus 4 seconds. And so final answer, and we expect this to be close to the speed of light. If you're not familiar with it yet, it's 3 times 10 to the 8th meters per second. We're not totally shocked to get a little bit different number just because it was an experiment, they're telling us. So 2.91 times 10 to the 8th meters per second. So close, good experiment, done probably 100 years ago. So not bad, 2.91 times 10 to the 8th meters per second. We're going to trust that works out. So two things going on here. The Michelsons experiment, understanding the apparatus and the basic idea of how Michelson performed his experiment. So I'll go back to that picture. This idea of this 8-sided mirror spinning around, that light bounces off, and in the time it took the light to go all the way to this plane mirror and back, we rotate the mirror by 1/8 of a revolution. Then the idea of these connections between the distance is related to the distance between the mirrors. It's not exactly the distance between the mirrors, but it's related to that. And then the time, which is related to period, which is in turn related to frequency. So depending on what information you're given, and the questions come from all different directions. Sometimes they're easy and you get the time for an 8th revolution. Sometimes you get the period and sometimes you get the frequency. But remember this kind of connection between the time, which isn't exactly the period, but it's related to the period, and how the period is not the same as the frequency, but they are related as well. So time to try a couple examples, see what you think, and see how you can roll with Michelson's experiment. Let's have one last look back just to appreciate historically this. So again, this is the real experiment, shining this light down this uber long tube, hitting some sort of mirror over here and rotating it like crazy so that it can bounce back somewhere else. So you can appreciate all the stuff going on, more complicated than the picture or the little cartoon view would lead you to believe.